Good evening. Welcome to the QCIS channel. On this channel, you get a daily dose of science, technology, engineering, and math. My name is Leon Jones, and tonight we're going to get into one of the FE topics, and that's called stoichiometry. Basically, when we deal with stoichiometry, it's chemistry. So you have equations like molarity equations. You'll utilize Avogadro's number, 6.022 times 10 to the negative 23. You have the balance equations. You're also going to have grams. You're going to have to take the molecular weight. So basically, you're going to utilize a lot of problems that involve dilution. Like if I have water, how much bleach or how much water is in bleach? You might be given grams, you might be given moles, and you're going to have to take one chemical to see how many moles in one chemical, and then you're going to do it for the other chemical. But first, let me share my screen, and I want to talk about what is stoichiometry. Now, when we talk about stoichiometry in chemistry, it's basically a quantitative calculation of reactants and products in a chemical reaction using the relationships found in a balanced chemical equation. Now, if you're taking the environmental FE or the chemical FE, you're going to see this. And if you're taking the other disciplines, so you need to listen closely. Why? Because stoichiometry, it involves basically determining the proportional amounts of substances that react, and they are produced relying on the principles of mass conservation and the use of molar ratios derived from the equations stoichiometric coefficients. That's stoichiometric coefficients. Now, here's a breakdown so you'll know of the key concepts. Balancing equations. These are the foundation of stoichiometry. Coefficients in a balanced equation represent the relative numbers of moles of each reactant and product, indicating the exact proportions required for the reaction to occur. Then you're going to have molar ratios. That's the coefficients in a balanced equation. They provide molar ratios, which are essentially mole-to-mole equalities between different substances in the reaction. So basically, these ratios remain constant, allowing for the equations regardless of the amount of reactants or products. Now, here's what you need to understand, because this can get confusing. It's how you apply. So basically, stoichiometry is used to basically calculate the amount of product that can be formed from a given amount of reactant. And then you're also going to determine the amount of reactant needed to react completely with another. You're going to find the theoretical yield and percent yield of a reaction. And then you're going to determine which reactant will be used up first in a reaction. That's the limited or the limiting reaction. And then you're going to calculate the concentration of solution. So basically, in essence, stoichiometry provides a mathematical framework to understand the measure of elements. It's from its Greek roots, stoichein. That's stoichein. Stoichein is meaning the element, and metron meaning measure, with a chemical reaction allowing chemists to predict and control the qualities of substances involved. Now, I'm going to go ahead and share my screen again, and we're going to get right into the PowerPoint. And we're going to talk about the basics of stoichiometry and mole calculations. Now, in this PowerPoint, you want to find out more, here are the links that you can find the information. Also, as I move on, here are some YouTube videos as well. And basically, again, this is an FE topic. I know I took the FE exam, and if you don't have basic chemistry down, this can be very difficult because you're basically using conversion factors. Now, the basics of stoichiometry and mole calculations. You're going to be dealing with reading and writing chemical equations, balancing equations. You have the types of reactions, formula weights and molar masses, percent composition, Avogadro's number, mole calculations. You're going to solve problems using dimensional analysis, using number one, Avogadro's number, number two, GFM, or number three, mole ratios from coefficients of balanced equations. Then you're going to determine empirical formulas and molecular formulas. And then you're going to have reactants known as limiting reagents. Now, chemical equations. Everybody understands chemical equations. Well, as I have one on the PowerPoint right now. Now you can see you have the equation and it is balanced. And how do I know it's balanced? Okay, because I have two right here, two hydrogens, and I have one oxygen. Now, well, actually two oxygen and four hydrogens. Now, when we talk about the coefficient is the number in front of the element. Now, if there is no number written, like I have O2, that means 1. So what you have right here is you basically have, if we want to talk the molecular weight, well, I already know oxygen is about, let's say, 16 grams. So you have 32 right here. So how do I know this equation is what it is? Well, you have your product and your reaction. So I have 2 here and I have 2 here. So if I go ahead and balance this equation, it is going to be balanced. Now, basically, you're going to have what we call symbolic representations or descriptions of chemical reactions, meaning of the symbols. You're going to have subscripts, parentheses, signs, arrows, coefficients, states of matter, reactants, products, catalysts, reaction conditions, use of particle diagrams, conservation of mass, chemical reaction equations. Now, reading balanced equations, this is what you need to understand. Well, you have your molecules, your particle diagrams, your mass, AMU. Now, what is AMU? Atomic mass unit. Now, where do you find that? On your periodic table. You're going to have your moles, that's your amount, and then you're going to have your mass. Then objective, what you need to do is find the smallest whole number ratio of coefficients for reactants and products that represent the law of conservation of mass. How? Trial and error to some extent. Now, you cannot change the subscripts in chemical formulas. Now, what is a subscript? I just gave you one. So if you have oxygen and you have 2, the 2 is the subscript. But because you can't change subscripts in chemical formulas, what you can do, you can change coefficients in front of the formulas. And you're going to do that when you balance the equations. Again, when you balance the equations, you have to look at those elements that occur in the fewest chemical formulas. So basically, you're going to move back and forth, checking the atom count each time a coefficient is changed. Then, you have an example right here. Example of a decomposition reaction that is used in airbags and cars. Now I have Na3, Na2. Now, if I wanted to balance this equation, I can look at it and tell you, well, you have Na, that's balanced, right there, but you have a 2, so you're going to put a 2 there. And then you're going to put a 1, and that's going to make it balanced. Or you have actually you have an N3, so we're going to see how to balance this equation. If I had a whiteboard, I'd actually balance it for you so you could see how it's actually done. So, practicing balanced equations. Here's an example of a equation. Now, again, you start with the element that occurs in the fewest chemical formulas. Formula weights, atomic masses of atoms, molecules, and formula unit, atoms. Example, Au is gold. One atom of gold has a mass of how many atomic mass units? You're going to calculate the formula weights in atomic mass units using the chemical formula and the atomic masses from, I just told you, the periodic table. Now, NaCl. What is NaCl? I can tell you what NaCl is. NaCl is salt. That's right. NaCl is salt. Now, what is C6H12O6? Those are very, very common. That's known as glucose. And glucose, guess what? That's sugar. So, percent composition. What is the percent carbon in C5H8NO4? That's the glutamic acid used to make MSG, which, what is MSG? Monosodium glutamate, used in a lot of Chinese food. And that's, if you don't know what it is, MSG is a compound that's used to basically tenderize meats and flavor foods. Now, again, what is the percent carbon in C5AHNO4? Now, what do you have to do first? First, you calculate the formula weight for the compound, and the compound is C5H8NO4. Step 2, percent composition. That's the mass of part divided by the mass of whole times 100. Or you get the percent element equals the number of atoms of that element times the atomic weight of the element divided by the formula weight of the compound times 100. So, what is the percent carbon in MSG? Again, they broke it up here. Now, you have C5H8NO4. Now, I already know what all 4 of those elements are. C is carbon, H is hydrogen, N is nitrogen, and O is oxygen. Now, I know hydrogen has an atomic mass unit of, let's say, 1.0079. Oxygen is 15.9999, and we can call it 16. So I know at least the O in this formula is going to be 64, and the H is going to be about 8. I don't know right offhand what carbon is, but I can find out if I had my periodic table. But I'm just going to break it down for you and go to step 2. You have to find the percent of carbon. That is the mass of part divided by mass of whole times 100. So what we're going to do is, again, what is the percent carbon in C5H8NO4? And that's MSG, the compound found to tenderize meats. So what we're going to do, I'm going to go to Avogadro's number and the mole, 6.02 or 6.022 times 10 to the 23rd. Now, the mole is a counting unit similar to a dozen, except instead of 12, it's 602 billion trillion. Or in scientific notation, which I like to call it, it's 6.02 times 10 to the 23rd. And that's in the honor of Amadeo, who studied the quantities of gases and basically discovered that no matter what the gas was, there was the same number of moles present. Now, if you had Avogadro's number of unpopped popcorn kernels and spread them across the United States of America, the country would be covered in popcorn to a depth of 9 miles. Now, the mole, M-O-L-E, is abbreviated as mole. Again, 1 dozen cookies, 12 cookies, 1 mole of cookies. And this is what Amadeo was talking about. No matter what the element is, everything is going to be 6.02 times 10 to the 23rd. And I'm going to prove it to you. Again, let's go back to the cookies. You have 1 dozen cookies, and that equals 12 cookies. You have 1 mole of cookies, and that equals 6.02 times 10 to the 23rd cookies. So you have 1 dozen cars. Well, 1 dozen equals 12. That's 12 cars. But 1 mole of cars is 6.02 times 10 to the 23rd cars. Then you have 1 dozen. What is Al? Al is aluminum. So that equals 12 aluminum atoms. So 1 mole of aluminum atoms equals 6.02 times 10 to the 23rd atoms. Now, note, the number is always the same, but the mass is different. So a mole of particles, again, contains 6.02 times 10 to the 23rd particles. So 1 mole of carbon equals 6.02 times 23, or we say 6.02 times 10 to the 23rd carbon atoms. What's H2O? Hydrogen and water, right? H2O is water. So we have 1 mole of water, and that equals 6.02 times 10 to the 23rd water molecules. Again, what's NaCl? NaCl is salt. So we have 1 mole of salt, and it equals 6.02 times 10 to the 23rd salt formula units. So technically, ionic compounds are not molecules, so they're called formula units. Now, you're going to have some ions and some cations. Now, 6.02 times 10 to the 23rd Na plus ions, and 6.02 times 10 to the 23rd Cl, which is chlorine, minus itis. Now, you're going to see this on the FE exam. I'm telling you. All right. Now, this is where we get into the good stuff. Gave you all the theoretic information on how you get it. So now, let's see how everything is put together so we can now apply it. So remember something. Avogadro's number as a conversion factor. So whatever we do to one side, we do to the other. So I'm talking about we're going to convert from one unit to another. So remember, 6.02 times 10 to the 23rd particles is 1 mole, or 1 mole is 6.02 times 10 to the 23rd particles. So note that a particle could be an atom or a molecule. All right, learning check. Number of atoms in 0.500 moles of aluminum. Number of moles. Now, what is S? S is sulfur. Now, what is found in sulfur? What if you smell sulfur? Where does sulfur come from? It comes from matches. So we have the number of S in 1.8 times 10 to the 24 sulfur atoms. Again, you can practice problems with and without a calculator. So how many hydrogen atoms are in 2.5 moles of water? This is something you can do on your own. Okay, the molar mass or gram formula mass, that's GSM. Molar mass or gram formula mass, GFM. So the mass of 1 mole is in grams, equal to a numerical value of the average atomic mass. Now, again, you get all this from the periodic table. So 1 mole of carbon atoms is 12 grams. 1 mole, what is Mg? Magnesium. So you get 1 mole of magnesium atoms, that equals 24.3 grams. 1 mole of Cu. Now, what is Cu? And I know a lot of these. Cu is copper. So 1 mole of copper atoms equals 63.5 grams. Now, other names related to molar mass or the gram mass formula or the gram formula mass. I like to call it the gram formula mass. It sounds much better. So we have the molecular mass, molecular weight. So if you have a single molecule, mass is measured in AMUs instead of grams. But the molecular mass weight is the same numerical value as 1 mole of molecules. Only the units are different. This is the beauty of Avogadro's numbers. Then you have formula mass, formula weight. Same goes for compounds. But again, the numerical value is the same. Only the units are different. Now, the point you may hear, all of these terms, which mean the same number, just different units. Again, find the molecular mass and gram formula mass. Usually we round off to tenths. So I have it right here. 1 mole of Br, which is bromium, might be bromium. Bromium atoms equals 79.9 grams per mole. 1 mole of Sn atoms equals 118.7 grams per mole. Again, practice problems. We can find out how many atoms of copper are there in a 3-gram sample of copper. So you have to utilize some interconverting mass and numbers of particles. Problems involving empirical formulas and molecular formulas. You have resources. PPT. Now, what is PPT? Now, you have ppm, which is parts per million. This may be parts per thousand. Then you have Pogel. Then you have practice problems. You know, what you need to understand with stoichiometry, just like physics, you have to practice, practice, practice. Just like you may have a problem that has H plus. Well, how do you find its pH? Well, chemical formulas of compounds. So basically, formulas give the relative numbers of atoms or moles of each element in a formula unit. Always a whole number ratio, the law of definite proportion. So NO2 means it's 2 atoms of oxygen for every 1 atom of nitrogen. NO2. What is that? It's called nitric oxide gas. 1 mole of nitric oxide. Again, we have 2 moles of oxygen atoms to every 1 mole of nitrogen atoms. So if we know or can determine the relative number of moles of each element in a compound, we can determine the formula of the compound. So types of formulas. We have the empirical formula. It's the formula of a compound that expresses the smallest whole number ratio of the atoms present. Then we have the ionic formula. They're always the empirical formulas. Then we have the molecular formula, and the formula that states the actual number of each kind of atom found in 1 molecule of the compound. So, to obtain an empirical formula, first, you must determine the mass in grams of each element present if necessary. Then you calculate the number of moles of each element. Then you divide by the smallest number of moles to obtain the simplest whole number ratio. So if the whole numbers are not obtained in step 3, multiply through by the smallest number. That will give you all of the numbers. Now, there's something you need to understand too in engineering. And you're going to see this on the FE exam too. Watch rounding, because you're going to be asked the number. And this is where I made the mistake on the FE exam. You're going to have several numbers. And you might not be given that exact answer. So there's going to be a word in there that's going to say nearly. Now, you have to look at nearly. you might have a number that's greater than that number or a number that's smaller than that number. So I generally would watch my rounding and watch my units as well, particularly if you're going to be taking the environmental exam. You need to know your units. If you don't know your units, it's going to destroy your chances of passing. And if you're taking a chemical exam for chemical engineering, same thing. It's not too much difference between the chemical and the environmental exams. So let's get into some of this now. You have a sample of brown gas. A major air pollutant is found to be 2.34 grams of nitrogen and 5.34 grams of oxygen. Determine a formula for this substance. Now, what are we going to do? We're going to require mole ratios, so convert grams to moles. So we have moles of nitrogen. We're already given the grams already, right? So we have 2.34 grams of nitrogen. So how do we find grams per mole? Again, you go to the periodic table. Now, what are we really doing? We're converting. So we're already given grams. So we go to the periodic table. We find out what nitrogen is. So then we take our grams of nitrogen and then we divide it by the grams per mole of nitrogen, and then we end up with moles. And we do the same thing for oxygen. We take oxygen. We're going to divide it by the weight. So we're going to go to the periodic table, and we're going to find out that we have one atom of oxygen, which is 16. So we're going to divide that by the grams per mole. And what are we doing? We're basically canceling out grams. So our empirical formula in actuality is a subscript, but we don't see the subscript. But when we write it in moles, we get nitrogen is 0.167 moles and oxygen is 0.334 moles. A compound has an empirical formula of NO2. Nitric oxide, the colorless liquid used in rocket engines, has a molar mass of 92 grams per mole. What is the molecular formula for this substance? Now, what are we looking for? Grams per mole. So what we're going to be doing is we're going to go the other way. So let's see what we can do here. Okay, we have a substance that has the following composition by mass, 60.80%. That's Na. What is Na? Na is sodium. That's right, sodium. Sodium. And I told you Br was bromine. But what is B? I know what B is as well. B is boron. Boron at 10.60%. And then we have H. So what is the empirical formula of the substance? Well, we consider a sample size of 100 grams. So this will be 28.60 grams of boron and 10.60 grams of hydrogen. So determine the numbers of moles in each element. Determine the simplest whole ratio of each element. Well, we move on. Determination of empirical formulas using combustion analysis data for organic compounds. Again, the experimental method that uses the mass of starting materials and masses of water, carbon dioxide used to produce, they're basically produced to solve for the empirical formula of organic compounds. Again, predicting quantities of products based on quantities of reactants use. So we have grams of reactants, moles of reactant, moles of product, grams of product. So let me ask you something. So when you have the equation, let's say you have small a, large A, small b, large B, yields small c, large C, plus small d, large d. Now, if I'm not mistaken, you have your reactants and your products. And I believe your products are on top of your reactants when you're actually dividing or using your mathematics. Now, like I said, I haven't taken chemistry in about 40 years, but I remember enough of it. So again, how do we do this? Well, predicting quantities of products based on quantities of reactants. Again, predicting quantities of products based on quantities of reactants. So the first thing you always do when you're given an equation, you have to balance the equation. Use the concept roadmap. Use dimensional analysis with molar mass, GFM. That's the gram formula method. Gram formula mass, and then the mole ratios as the basics of the conversion factors. Again, it's a practice problem. The decomposition of potassium chloride is commonly used to prepare small amounts of oxygen gas in the laboratory. How many grams of oxygen gas can be prepared from 4.50 grams of potassium chloride? That's a practice problem. And then we have limiting reactants, or we have limiting reagents, which are reactants problems. So we start with Hovel limiting reactants. Again, start off with a balanced chemical equation, determine moles of reactants, set up tables, initial change and end final or ice charts. Identify the limiting reagent or the reactant. And then you finish the problem using dimensional analysis. And again, what you do, and this is for the FE exam, is you're going to have on the FE other disciplines, on the FE chemical, and on the FE environmental. You're going to have at least 7 questions of chemistry. Now, for your environmental and your chemical exams, you really need to know chemistry. You don't need to know it as much on the other disciplines, but on the other disciplines, and I'm going to get into the types of FE exams later on and what you need to know and what you should be studying. But generally, these 3 exams, you need to know the chemistry. Chemistry is a lot of points. It's 7 to 11 points. So finally, again, you understand that this is chemistry. You have to do problems. These problems are going to be used in the lab, but know how to utilize the conversion factors, know how to use the periodic table, and use the updated periodic table. I know when I was in school, we only had 103 elements. Now there are 118. So you need to know what's being asked. This is why I can, from memory, give you an idea of what some of the items are, because I've seen them before. But you need to understand Avogadro's number, because it's going to be very important. And even if you're not taking the FE exam, let's say you want to go into medical school and you have to take chemistry, or you want to get certified by the American Chemical Society, you're going to have chemistry on the exam. Now, again, as I am telling you, engineering is basically made up of 3 different sciences that adds math to it. It's biology, which is a life science, and then you have chemistry, and then you have physics. And then what makes it engineering is you combine those sciences with all of the math. But you need to understand moles, grams. You need to understand the periodic table, equivalent weight. You're going to see that. Bottom line, when you understand what the problem is asking, because basically the problem is they already give you what you got. So they're trying to, and that's the first problem. You have this, but what do you need to get this? So the second part of the problem is what you need. The first problem is what you have. And if you think about that in layman's terms, it's going to be easy for you to get the problem right. So if they're asking you for grams in the problem, you already got grams. So what's the next step? They're going to ask you to convert because you want to get moles. So what are you going to do? You're going to go to the periodic table, and below in your denominator, you're going to divide by grams per moles. Why? Because you have to cancel the grams, and then you get moles. And the best way to really start these problems, even before you balance equations, now this is something they don't tell you either. You take each part of the problem. Let's say you have salt, NaCl, okay? Start off with one atom or even two atoms. So you're going to take Na, which is your sodium. So if you're given grams of sodium, then you're going to go ahead and look under Na. So you already have, let's say you have 4 grams of sodium. What is it in moles? Well, what I'm going to do is I'm going to go ahead and let's say I got 4 grams of sodium. So whatever sodium is, let's say sodium is 12. So how am I going to find that in moles? I'm going to definitely divide by 12. And what do I got? 0.333 moles. That's the beauty of it. And then vice versa. Because basically that's what stoichiometry is. You're basically utilizing reactants and products. And when you understand those concepts, you're going to see those, when you see those problems on the FE exam, you'll be able to solve them. Because remember, on the FE exam, you have to solve a lot of the problems in about 3 minutes. And you think that time is long? 3 minutes, you think about it. The 2 hours goes by really quick. And you don't want to waste time on a problem that you can't figure out because you have other problems. But basically, what I have done is give you an overview on stoichiometry. And again, stoichiometry, as I share my screen, you need to know we're basically dealing with a quantitative calculation of reactants and products in a chemical reaction. We're going to use the relationships found in a balanced chemical equation. And it also involves determining basically the proportional amounts of substances that react and are produced relying on the principles of mass conservation. And we use the molar ratios derived from the equations stoichiometric coefficients. And always the coefficient is the number in front of the element. If there is no number, it is a 1. Because you need the coefficients to always balance your equations. And that concludes this topic on stoichiometry. If you like what I just presented, please comment, share, and subscribe. And if you're looking for some political and social content, check out my main channel, the 401 Talk Zone Radio Show channel. Now, here's where you can find me. For the QCIS channel and the 401 Talk Zone Radio Show, you can find me right here on YouTube. Now, for the QCIS channel and the 411 Talk Zone Radio Show channel, you can also find me on X, formerly Twitter. Now, here's where the differences are. 01 Talk Zone Radio Show. You can find me on Rumble, and you can always find me on Truth Social. And for the QCIS channel, you can find me on LinkedIn. Once again, thank you for viewing this content on stoichiometry and calculations right here on the QCIS channel. On this channel, you get a daily dose of science, technology, engineering, and math. Until next time, my name is Leon Jones. I want you all to have a wonderful and gracious evening.